Welcome to my talk. My name is Lukas Wessels and I'm a PhD student at TU Berlin under the supervision of Wilhelm Stannard. I'm working on optimal control of stochastic partial differential equations, and in this talk I'm going to present Peng's maximum principle for SPDES. This is the setting for my talk. The cost functional J consists of running costs L and terminal costs H, and the state evolves according to a stochastic reaction diffusion equation with nonlinearity B and diffusion coefficient sigma. B and sigma are assumed to be Lipschitz continuous with respect to the state variable, and the control U enters both the drift and the diffusion. The equation is driven by a cylindrical Wiener process W, and we consider the equation on a one-dimensional space domain, so lambda is just an interval. Our goal in this talk is to derive a necessary optimality condition. Let me briefly recall the history of the problem. In 1956, Pontryagin proved his famous result, the Pontryagin maximum principle, which is a necessary condition in the finite dimensional deterministic case. After that, there were many generalizations to the stochastic case. However, it was not until 1990 that Peng proved the full generalization to the case where the control U also enters the diffusion coefficient. Since Peng's result, there were many generalizations to the case of controlled SPDES, but all of these works had at least one of the following two drawbacks. Either sigma was independent of the control U, or there were strong assumptions imposed on the coefficients of the cost functional, excluding in particular quadratic costs and Nemitsky type costs. Our goal is to close this gap. Now I'm briefly going to recall the proof of the maximum principle. Let U bar be an optimal control, and then we define a so-called spike variation U epsilon. And U epsilon is equal to U bar everywhere, except for a short time interval between tau and tau plus epsilon. In this short time interval, we define U epsilon to be equal to V, and V is an arbitrary element in the control domain. Since U bar is an optimal control, U bar minimizes the cost functional. That's how we get this inequality. And then if we plug in the definition of the cost functional, we end up with this expression. In order to prove the maximum principle, one has to perform the following steps. First, we employ Taylor expansions for the coefficients of the cost functional. Then we divide the whole expression by epsilon, take the limit epsilon to 0. And then we want to identify all the remaining terms. In the deterministic case, it is sufficient to consider Taylor expansions up to order 1. However, in the stochastic case, because of the Ito correction term in stochastic calculus, one has to consider Taylor expansions up to order 2. And in these Taylor expansions, we encounter these quadratic terms. Here, by y epsilon, I denote the linearized state equation. In order to introduce the adjoint state, one has to define a linear functional. One already encounters these quadratic terms in the finite dimensional case, and Peng had the idea to replace the quadratic term by the tensor product. And then he derived an equation for the tensor product on the space of n by n matrices, defined a linear functional, and then defined the adjoint state using Ries's representation theorem. If we want to follow the same route in the infinite dimensional case, we can identify the tensor product of H with the space of Hilbert-Schmidt operators on H. Then we can derive an equation for the tensor product in this space. However, this is not sufficient to perform the duality analysis. For the duality analysis, we have to solve this equation in the space of trace class operators. But this space of trace class operators is only a Banach space, which leads to several technical difficulties. And our idea is instead to use the explicit representation of the state space. Our equation is set on the L2 space. So we can identify the tensor product with another L2 space, Now this is the space of square integrable functions in two variables. And if we have two functions y and z, the tensor product is identified with a function that maps lambda and mu to y of lambda times z of mu. If we use this idea now for this quadratic term, we can write the tensor product here, but then we have to introduce this operator delta. And delta takes a two-parameter function and evaluates it on the diagonal. However, in order for delta to be continuous and well-defined, we have to impose some regularity assumption on the two-parameter function. We define this operator delta on the Sobolev space H10, and then this term is linear and continuous in the tensor product, and we can again use Ries's representation theorem to define the adjoint state. And this adjoint state, which I denote by capital P, now is also a two-parameter function. Furthermore, we can derive an equation for capital P. This is now a backward stochastic partial differential equation. But notice that in the drift, as well as the terminal condition, we have the adjoint of this operator delta. And you remember the operator delta operated on the Sobolev space H10. So the adjoint maps to the Sobolev space H-1, the dual space of H10. And H-1 is the space of distributions. So now we have a backward SPDE with a distributional terminal condition. However, one can still show that the first part of the solution, the adjoint state P, is still function valued. It lives in this space. And this representation as a function can be used to derive the maximum principle. The maximum principle for SPDEs states that an optimal control U bar minimizes the generalized Hamiltonian over the control domain for almost every t and almost every omega. The generalized Hamiltonian here is formally defined the same as in the finite dimensional case. However, notice that for the definition, we need the second order adjoint state. And the main point of our main result is that the second order adjoint state is characterized by a backward SPDE, and it is characterized as a function. Okay, I'll wrap up my talk with an overview of the references. The first reference is Pontryagin's classical result in the finite dimensional deterministic case. The second reference is Peng's generalization to the case of controlled SDEs. This is the paper that I presented in this talk. And in the introduction, you can also find more references regarding this problem. And finally, I want to mention another application of our result. This characterization of the second order adjoint state as a function can also be used to derive a relationship between dynamic programming and Pontryagin maximum principle. Dynamic programming is the second major approach to optimal control problems. And in dynamic programming, one defines the so-called value function. Now we are able to show that the second order viscosity differential of the value function is related to the second order adjoint state that I introduced in this talk. This is work in progress. And yeah, if you have any questions regarding my talk or if you have any comments, I'm happy to discuss at the conference. Thank you very much.